We're going to talk about how to draw organic structures, and this is going to be kind of one of the big topics. You can just keep numbering it down. There's what it is, so if we run out of space. And so this is going to be what you guys are going to be expected to be able to draw when I ask you guys to draw different molecules and Lewis structures and that kind of thing. So we're going to take all the ideas and stuff from what we've been talking about and kind of translate it into a shorthand notation for how we draw structures in organic chemistry is what it is, okay? So we'll get into that. So I think we're going to kind of dip our toes a little bit into chapter 2 and chapter 4 here is what it is, all right? Sound good? Mm-hmm. Okie dokie. So with respect to the lab, it looks like everyone's kind of getting through with the, at least the synthesis part of what we need to do in the lab there. And then next week we'll come in and we'll do the rest of the analysis. And we'll be talking about that before you guys get in the lab next time also, right? So that's kind of where we're headed with this. We'll need to know what functional groups are, right? And then we can talk about how we measure those in the lab there. Sound good? Cool, all right. Yeah, and if you guys just keep numbering down the column there, whatever it is, and then we'll go with it. Okay, questions about that stuff before we get started then? Everybody got it? For those of you guys who walked in late.
Swim practice.
No. What? Excuses? What in the back? What? I'm just kidding. I'm joking. I'm passing around a little attendance notebook, so make sure you guys just kind of put your name on there and that kind of stuff. Okay. Make sure I can read it. I'm not a wizard. Okay. Yet.
There are a lot of people
We'll just
missing.
put our signature. It'll be a scribble.
Huh?
We'll just put our signature. We'll sign it as a scribble. For one more thing.
I'll put that you guys didn't attend.
Also,
and then I'm gonna call your mom.
you have been telling
Please
me
call my mother. I want to see that interaction.
Is that another lie, Doctor?
What? That I'll call your mom?
No, that you're a wizard.
Oh.
You just said you weren't. You've been telling us for 2 weeks.
Yep.
that you're a
Anyway,
wizard.
so we'll get started with some prayer, and then we'll finish up kind of our thoughts here on this and launch into it. But Lord, we just thank you for another chance. We thank you for another opportunity, and we just thank you for another day, Lord. Just because as we move into the weekend, at the end of a long week, Lord, we just pray for, just understand how to rest in you, Lord, as we look to take some time off from our work and these things, Lord. So help us just understand what you mean when you talk about the Sabbath in Scripture there, and just how Sabbath was made for man, Lord. And just we look for understanding that come from you. We know that wisdom starts with you, Lord. So for the things that we have laid out before us, for the things that we have to do today, Lord, we pray for your strength and wisdom just to guide us through that. We just pray for you to walk before us, Lord, and just give us the path that we should be following. And we ask all this in your name. Amen. All right. So we were talking about hamburger buns, right?
Yes, sir.
And we had come up with the idea about the relationship between hybridization and pi bonds and structure and all that kind of stuff, right? And so we had said that as we have hybridized or unhybridized p orbitals, that is where we start to see our pi bonds come in, right? We talked about paint buckets, and we talked about if you're sp2 hybridized, you can have one pi bond, typically. And if you're sp hybridized, you typically see two bonds come out, two pi bonds come out of it, right? Yeah.
In biology, Dr. Surson said that lithium has an sp cubed bond always.
Well, I'd have to see the context that he's referring to that, but anyway, so the metals deal a little bit differently, is what it is. So remember, I told you that hybridization is kind of all baloney,
Yeah.
right? But useful baloney, right? So
Fair enough.
there are some different aspects to this. Oh, didn't expect it to start raining already. Geez. Anyway, Florida, man. So the point being, I tried my best to draw crappy hamburger buns for you guys here to represent the pi bonds. I know there's much better depictions of that in the textbook. So take a look at that, right? They have nice, rendered graphics and all that kind of stuff. Way, way, way better for you guys to be able to kind of make sense of these kind of things here. Now, do I need you guys to be able to draw these? Probably not, right? What I need you guys to understand is that when we have a pi bond, its density is above and below, right, or the front and the back, right? It's above, below, front and back, the plane of the atoms themselves, okay? Sigma bonds are in between atoms, the hamburger bonds are on the outside, the pi bonds, okay? And that's going to kind of help explain why we tend to see pi bonds react more frequently than sigma bonds. That's not the only reason, but if we're just kind of contextualizing this within the idea of electrons doing chemistry, electrons on the outside of things get to interact first, okay? So that's the whole idea there. You guys following along with that, what I mean, right? Just we have to know where electrons are. That's step number one, okay? Good? All right. Oh, there it is. Okay. Okay. Draw that. Draw me the proper structure with wedges and dashes and all that kind of stuff.
Hey Doc,
Mm-hmm.
are alkanes 2 and plus or minus?
Are alkanes 2 and plus and minus?
Like and 2 and the, never mind. I know what I'm talking about, but I don't think I
Okay.
can explain it to anyone else.
Oh, we almost caught you on camera. It's all good. It's all good. And you got caught in the rain too, right? Oh no. Rough morning. Good? Everybody got it? What's it look like? Let's see here. You're not done? Oh man.
I just drew a line.
You drew a line. Let's see. How are we doing? But that's fine. So what you're saying is I can openly mock your work then, is that what you mean? Oh, okay, that's all I really care about. All right.
The dashes go up and down. Do the dashes go towards the paper or away from it?
Dashes?
It doesn't matter.
Dashes go away, right? They're always saying into the plane. All right, so I didn't see anybody have the right answer. Oh my gosh, what's wrong with you guys?
What? Wait, no, I got the right answer.
What?
Yeah.
That's not it.
Well, it's
That's
close enough.
that's because you copied my work.
Sorry, Maria. There's no justification.
So if you take a look in the textbook, right, they'll give you an answer like this. Okay? Now we're going to have to learn a little bit about some of the methods behind the scenes here, okay? Now what I did see is I saw some answers that looked like this, right? Okay.
How is that different?
How is that different?
It's not.
It's not. It's the perspective thing.
Oh, because the.
It's not a perspective thing.
No, because Marie, look, is it the office? The
So
one's up and one's down.
we have to be careful, and this is something we're going to talk about in a little bit here, right? Now, if I ask you guys just to draw me the proper molecular structure for this, either one of those are fine, right? But as we'll soon find out, one of those is better than the other. One of those is lower energy than the other, okay? So what we're going to have to get into here very quickly is the idea of visualizing how these molecules actually look. Now, why am I telling you guys this? Because if you remember, I think it was 1 or 2 classes ago, I said, hey, right? If you guys have trouble visualizing things, you're going to have to get better at it. Get a model kit or whatever it might be, okay? So we're really going to get into this part. We're going to talk about rings and flips and all this kind of stuff. So if you guys want to start bringing your model kits and things, it might be helpful at this point, all right? But there is a difference between those two, and we'll talk about what that is, right? But for the moment, if you guys drew either one of those, that's just fine. Sound good? What's the hybridization of each of the carbons?
SP.
3. How do you know?
Because it's touch. Yeah, the touch would be cool.
How else do you know?
Because there's only sigma bonds.
How many? 4. If I have 4 sigma bonds, I need how many orbitals? 4. And what's the only hybridization that gives me those 4 orbitals? Got it? You guys with me on all this, right? What are the idealized bond angles in there? 109. Is this a flat molecule?
No.
No. Got it? Did it take a long time to draw this? No. Oh, okay, good. You guys said no. Let's keep going then. All right. Oh my gosh, Dr. H, it took forever. Okay. Let's see, how big a jerk do I want to be? Yeah. The answer is huge. All right. Okay.
Friday, dog. It is 8 o'clock on Saturday morning.
Yep. So you guys should have been awake for at least 3 hours at this point.
What?
We're college students. We work late into the night and get up as late as possible.
I mean, speak for yourself.
Man, it's a hard night watching Pixar movies. I understand.
I wish I was.
Yeah.
Can we watch a Pixar movie instead of doing?
Can we please?
I'm
Yes.
basically like.
Let's watch Inside Out.
Look, I'm basically like. I'm basically like a Pixar movie here, right? So.
No, that's
Yeah, except you don't make us
Hyper
feel
realistic. Okay, everybody got it? All the wedges and dashes, you all done? What?
Patience is a virtue, Dr. H.
It's true.
Yeah, so it's something I should aim for, but might not have right now. Faster. There's a lot of carbons, huh? There's a lot of hydrogens, right? There's a lot of wedges, there's a lot of dashes, there's a lot of this, there's a lot of that. Okay? So as you guys are going through this, let's see what we can do. Okay, there's my excellent hairy caterpillar drawing here. Okay. How many of you guys got that?
That's close enough.
I drew it.
No, I believe you. Does everybody see why we drew things like this? Remember, when we're drawing something on paper, okay, we want to try and represent as closely as we can to what the actual structure is, okay? You guys following along with that? Now, how long does it take to draw this? Couple minutes, maybe right now. We'll kind of whittle that down as you get more practice. But it took too long for me, okay? Now, I'm never going to call myself lazy. What am I going to call myself?
Calorically efficient.
Calorically efficient, okay? That sounds good enough. You can put that on the resume, right? Or time efficient even also, right? So I want to develop a shorter way of drawing these molecules. Because relatively speaking, C5H12, right? That's not that complex a molecule, right? We're going to be dealing with much more complex things as we go through, okay? I'm going to ask another important question. What's the hybridization of all the carbons? They're all sp3. Is this a flat molecule? No. Are the hydrogens there? Yeah, I see him, Dr. H, okay. These are important questions and we'll start to see why in just a minute, okay? Because what we do when we develop our shortcut method is we leave some things off. And when we leave things off, we tend to forget them, okay? I forget the name of this phenomena, right, but it's it's something that happens in movies, right? It's basically when something's not on screen, we're not looking at it, is kind of what it is, right? So the same thing's gonna happen here, right? So we're gonna leave things off and we're gonna forget about it, because we're like, yeah, they're not there, and then we miss points, okay? Okay, so what are we gonna do? Well, one thing we can do is kind of start to simplify things a little bit. So if I take each part here, okay, and kind of condense this down, we can translate this into CH3, right? CH2, 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 right? And CH3. So sometimes you'll see things represented like this, okay? You guys with me on that? What did I it made it easier, right? It made it quicker to draw. What information did I lose? I lost the shape of it. Got it? Did I change anything though? Is the molecule any different? No. Is everything still sp3 hybridized? And is it right? You guys get what I mean with this? So we lose structural information, but what do we gain? Precious, precious time.
But it's
Right?
it's a representation.
Right. And so this is the point, right? We have different representations that we can use at different times. Everybody with me though? Right? So I think they call this like the condensed, a condensed drawing in the textbook. I forget the actual term, and I forgot to look it up before I came down. So I'm pretty sure they call that just the condensed way of drawing things. Okay, good. Well, that still took too long. I don't like to write C's and H's and 3's and 2's and all that kind of stuff.
Why are you a chemist then?
Huh?
Why are you a chemist then? That's kind of a good
Because
job.
I'm too dumb to be a physicist. That's why. They're way smarter than I am. So.
What's
So
the
if I-
hierarchy of science?
Dr. H number 1, everyone else number 2. Okay. So if I label my carbons in orange there, okay? So what I'm going to do is I'm going to abbreviate by making each carbon, or let me do it this way instead, right? So everyone follow along. There's my carbons. Here is how we're going to more accurately and quickly represent what we have. Okay?
Absolutely.
You guys with me so far? Right? We made everybody's drawing of a bird when they were, like 4 years old. Okay? Right? You guys with me? They have little wings and.
Yeah.
It's
It's
not
not It's a beautiful bird, Dr. H. We're proud of
It
you.
needs to be more
Right.
curvy if you want it to be a bird.
So here we have our line stick notation, our shorthand, our stick structures. There's a couple different terms for these things. But this is predominantly how we're going to start to represent things. Okay? So watch, here's how we have to break this down. At the beginning and end of every bond, okay, that's where a carbon is. Okay? At the beginning and end of every line that we have, that's where a carbon is. Good? So same set of questions I was kind of asking you guys to look at before. What information did we lose when we went to this stick structure notation here?
The three-dimensional shape.
We lost some of the three-dimensional shape, right? But you see how we tried to maintain at least how the skeletal structure of the carbons are bound together. Everybody with me on that? Okay, we are in organic chemistry, right? We are looking at the chemistry of carbon. So we try to maintain that side of the structure at least. What did we lose though? Yeah.
We lost the hydrogens.
Okay,
But
did the hydrogens magically disappear? No. Hydrogens on a carbon are understood, okay? So when we do our abbreviated drawing, right? When we do our abbreviated drawing, hydrogens bound to a carbon are understood. Everybody with me on what I mean with that? We fill in the missing number of hydrogens because we understand how carbon reacts and how carbon forms bonds. Got it? Okay. We have to represent every bond between atoms though. Okay? So our blue lines here represent single bonds. And we'll walk through an example just a little bit about double bonds and triple bonds and those kind of things. Okay? But starting out, the simplest of drawings with just carbons and hydrogens. Okay? Everybody understand this? All right, so let's go in the reverse here then. Let's see what we can come up with. Okay, so take this and translate it into a complete molecular structure there. Okay, so work in the reverse. We went from here to here, go from here back to here. Okay? You don't have to do the wedge and dash stuff, I mean, if you want to, that's fine, but it's up to you. That will take a long time. but fill in the number of hydrogens on each carbon that you guys have drawn, right? That's the important thing to recognize. So we just have a carbon with no hydrogens on it? Mm-hmm. So we'll talk about that in a little bit. Yeah, for now it doesn't really matter. All right. Well, looks like we're all headed in the right direction there. So we'll talk about it. For right now, it doesn't really matter. But yeah, either way you guys want to do it. Okay.
No double bonds, right?
No, none here, right? So just to color code things, at the beginning, at the end, where two lines come together, right, that's where our carbons are, right? So just to kind of mimic things, carbon, 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 carbon. Right, and then we can just bring this all together. Good? Everybody with me on that? Okay. Remember, we explicitly show bonds between carbons and other atoms aside from hydrogen. Good? So explicitly we see one bond here from this carbon, so that means how many hydrogens need to be here? 3, got it? Looking at this carbon here, right, we see 3 explicit, so we have 1, right? And I'm ran out of space here, but hopefully you guys can see 3 up there, 1 right here. All right, let me just make this a little bit more accurate. Good? Not too bad, right? Pretty simple, pretty straightforward way of representing carbons bound to other hydrogens. Okay? So you guys will get tons of practice with this as we go through for the next year, right? But if you guys are feeling a little bit shaky at the moment, that's fine. Go practice it some now, right? Got plenty of time. Fair? Yep.
When do we start naming these?
Soon. But not yet. Don't worry, the misery is coming. Okay?
It always is.
It always is, right? Even scripture talks about that, right?
That one's
Okay. See how this changes your world. Yep. Translate from the shorthand to the what we were doing before there, right? Draw out all your hydrogens, all that kind of stuff. Good. 5 carbons. Carbon, 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 carbon. Single bond, double bond, single bond. Good. go through the same assessment. So when we get to a double bond though, what do we have? We already have 3 bonds here, so how many hydrogens are coming off there? Only 1. Let me just change colors here for just a second, just to make a point. Okay, what's the, let me do this here. Just so I can start talking about things. What's the hybridization of my orange carbons?
SP3.
sp3, right? What's the geometry of all my orange carbons? Tetrahedral. What are the angles there?
109.5.
What about for the black carbons? sp2, okay,
120.
120, trigonal planar. Are there any wedge and dash things coming off of those black carbons? No, there are not. They are planar. If you're in a plane, do you have things coming into or out of the board? No, usually not for what the stuff that we're doing. Got it? So if you put a wedge bond here for that red hydrogen, that's probably not going to be correct, okay? Unless you have a very unique perspective on how you're rotating that molecule there, okay? Everybody with me on this? If you're planar, you're planar. If you're flat, you're flat. That's all it is. Good? All right. So, let's see, what do I want you guys to do? I want you guys to draw this for me, okay? Using the shorthand notation. Good?
We already did that one.
Yeah, that's the one we just.
Oh, Dr. H, you made a mistake.
He never makes mistakes.
Who makes mistakes around here, huh?
Us.
I want you guys to draw that for me, okay? You guys were itching for that. Ooh, did I set you up? I put that ball right on that tee for you guys, and you whiffed. Let's see what you guys come up with. Draw C5H12 for me. Ah. Yes, I always am. But there's a purpose for it, I promise. Ah.
Aha. Aha.
Aha.
Aha. Got it.
Oh, frick.
Aha. There it is. I like that. I like that moment where it clicks over.
Yeah.
I like that moment.
Wait a second. I'm confusing myself.
You're shopping while you're in class. No, I'm just kidding.
Yeah.
Okay? So, there's C5H12. How many of you guys got that?
Say what?
That can be one form of it.
That can be one form of it, right? But you guys might have done that, right? Or you might have done, whoops, or you might have done this, right? Oh, I see now, Dr. H. There are multiple ways of drawing things. What's the relationship between all these? Not resonance, because what? We didn't move electrons. What did we move?
Atoms.
Atoms. We have different connectivity between things. Right? So we have constitutional isomers. Same formula, put together differently. Okay? Same formula, put together differently. Constitutional isomers. Can you guys translate each of those three into the carbon-hydrogen drawings? right? That'd be good practice, especially the first one I drew up there, right? What am I trying to get you guys to look at with this? The main thing I'm getting you guys to try to pay attention to is how we can make different shapes and connectivities with carbon, okay? Carbon can have up to 4 bonds to it. We can have a lot of different ways that we can make those 4 bonds. So I don't want you guys to get locked into just thinking, oh, we only have these linear type structures, okay? That's a very common, let's say, fallacy of organic chemistry, okay? Only things come in straight lines there, right? That's not quite the same, that's not quite what we need to do, okay? Not how we need to be looking at things. You want me to trick you guys again? Too bad, I'm gonna do it. Yeah, I like for you guys to think that you have a chance, right? That's true. All right, so I'm gonna ask you guys to think about this one, okay? If you guys have been reading ahead in the textbook, then you already have some of the answers, okay?
Yes.
Let's see, we have 1, 2, 3, 4. There's probably, just on a quick count, there's probably 12 different ways you can draw this. Do I have to learn, Dr. Aiden? See what you guys come up with, though. Think a little bit.
Wait,
Work with
how
your-
many ways did you say there were?
Off the top of my head, there's quite a few. I think I'd have to double check and write it all down, right? But there's plenty. See what you guys can come up with.
It's an alkane, right? Will it always be an alkane?
Oh, now I got it here. Good, very good. Look. No, I appreciate this. I'm just saying, everybody says they don't like puns. But, you know, I disagree with it.
The porpoise one yesterday was pretty bad.
Oh, I've got years of practice.
No, actually, that was really interesting.
Okay, but Yana, imagine if Dr. H ever gets married and has children. Like, imagine the dad jokes that those poor children will be exposed to. That's like.
So, what is different between this and what we had previously? Well, we lost 2 hydrogens, right? If we don't have bonds, there's a big mosquito in here. All right. Well, I'll leave a present for somebody else. Right? Right? So we lost 2 bonds to hydrogens. So we have to make that up in some way by adding bonds to another carbon instead, right? Because we still have to maintain that all carbons have 4 bonds. You guys follow along with what I'm saying there, right? If we remove 2 hydrogens, we have to make extra bonds between carbons. So let's say, maybe the first way we might think of is by putting a double bond in there. Good. Go through, check to make sure I didn't make a mistake. 5 carbons, we can count up our hydrogens, right? So I'll just quickly kind of sketch them out here. We'll do it in blue, right? So hydrogen, 2 hydrogens here at the end, hydrogen, hydrogen, hydrogen. Now, while you guys are writing this down or thinking about this, it might be good practice to go back and ask yourselves the question, what's the hybridization of each of those carbons? You know, what's the geometry? What are the angles? All these kind of things with that, okay? Until it just kind of becomes second nature to go through and think about that stuff. All right? Everybody with me on this? Here we go. What else can we do? Is this a different molecule?
Yes.
Yes. Did we change the connectivity between atoms? Yes. Okay. Is the double bond in a different place? Yes. Is this a resonance structure? No.
No?
No, it is not. It's a different molecule. My double bond here was between the carbon at the end and the second one in, right? Here it's between the second one and the third one, right? Different connectivity. Yeah.
Would the resonance structures be between?
There are no resonance structures. Please.
Oh, because the hydrogens have to move around too?
Right.
Okay.
It's the atoms moving, not just the electrons.
Correct. Correct. And this is the point, right? So what you guys were just discussing there, right? Remember, we lose information when we draw this shorthand. We lost where the hydrogens are. Okay? They're not gone. They are there. Okay? Now think about this for a second. Is this a different molecule? No. Okay? You guys, all of us in here, just by habit, because of where we live, where we grew up, we're used to reading things left to right. Yeah? So watch, I said this is between number 2 and number 3 here, because I started numbering over here. What if I do 1, 2, 3? Right? Is there anything wrong with doing that? Now you might say maybe, Dr. H, because I don't like doing things from the right to left. Okay? Now we're going to talk about how we can name these things, and that's going to be important to recognize. Don't just get in the habit of looking at things from left to right. Okay? Look from right to left, top to bottom, all the different dimensions. Remember, we're dealing with 3-dimensional molecules. So you guys need to be starting to look at things in 3 dimensions. Got it? Everybody with me on this? So are these different molecules? No, those are the same, right? Just like those would be the same here, right? You guys with me on that? So they just kind of look like exact mirror images there, right? So that's a change in perspective, so to speak. Are we done?
No.
No.
Far from it, right? There's one, right? There's one. There's one. Right? Yep.
In terms of when you're drawing in the double bond, is there a specific side on which we should be drawing it, or does it matter at all?
Like top versus bottom?
Yeah.
No, it doesn't really matter. Just by convention, I think it's on the bottom, but it doesn't make that much of a difference.
Are those last two that you just drew really, or rather, never mind.
Okay. Good? Are we done? No? Ooh. Now we start to get into our discussion about rings. Okay? Take this and translate it into this. Okay? Take your nice pentagon there. All right, see if you can translate that into the drawing with carbons and hydrogens. What's the geometry of all those carbons? What's their angles? What's their hybridization? Yada, yada, yada. Is that a flat ring? No, it is not. Does it look flat because of the way we drew it? Yes, it does. Is that a flat ring, though? No. Okay, this is extremely important. Okay? Don't trick yourselves. Okay? It's going to be very important to be able to recognize that that is something that has three-dimensional shape. All right? Are we done? No. I'm done though, Dr. H.
Are we ever truly done?
No. Okay. I could do that, right? I could do this, right? I could do, oops. I could do something like that, right?
In this class?
Yes, 100%. Thank you.
So we have linear structures and we have ring structures. Ring structures is maybe a little bit self-evident, right? It's basically where the carbons wrap around back onto themselves. We're going to be talking about these quite a bit. They are extremely important structures. Okay? Lots of different types of rings. We're going to talk about how they react, how they behave, what happens to their geometry, all this kind of stuff. Yeah?
For those last couple that you drew, does it matter where the line is? Like for that square with line coming out, does it matter what part?
Good question. Draw a different one and answer. See if you can answer that, right? Does it matter where I put that group coming off of that square, right? That's kind of tricky one to answer, right? If you imagine it just be a rotation, right? And so that's just a change in perspective. We still have the square, and we still only have one thing coming off of one of the carbons, right? So they're all going to be equal, right? But try and convince yourself of it, right? Everybody with me on this? Let's do more.
Yes.
What's up?
For the square one, if it was on a different one, wouldn't it just be a change in perspective?
Yeah, that's what I was saying. Yep. Okay. Let's see here.
So on an exam, if you just give us a formula like that, are you going to be very specific about what you want us to draw? Or are
Maybe.
you just going to draw as many structures
Maybe.
as what it is?
So now we probably have somewhere closer to about 40 different isomers that we could draw.
Ugh,
Probably even more than that I'm forgetting.
God.
Let me take a quick peek if we can find the answer online here just to get an exact answer. See how many. $44 is what they're saying. All right, everybody got all 44 answers?
Absolutely.
So remember, now we kind of bring in the tool of rings. Okay? Start to see a little bit where the fun of organic chemistry comes.
You call this fun?
Oh yeah. Hey, like I always say, organic chemistry puts the fun back in chemistry. There's only science, no fun. All right? Count how many hydrogens there would be in that.
Oh. Is this
I hope that got picked up on the recording, Jill.
Wait, what? Jill, what did you say?
What in the world did I draw here?
What?
A chaise lounger?
Is that a triple bond?
Aha. How many? See if you guys can translate that into the carbons and hydrogens, okay? What's up?
Is this an acceptable notation?
I wouldn't recommend doing that, but yeah, it's okay-ish, yeah. So just be careful because, you know, you're showing two things coming together and then a CH coming off like that. That can actually mean a couple different things, so I wouldn't do it that way, right?
That makes sense.
Everybody okay on this one? Why did I draw it looking so weird? What's the geometry here?
Linear.
Linear, so what's the angle?
180.
180. Remember, when we're drawing our carbons, we want to represent it as closely as we can to how they actually are, okay? I don't have many pet peeves in life, but one of them is when students draw that. Ew! Ew! Okay? Because what are you guys telling me? That we have a 180-degree angle, but I wanted to, you know, draw not 180, okay? Are you guys technically wrong with drawing it like that? No. Am I gonna really take points off in an exam for that? Yes. No, I'm just kidding. Anywhere I can find, right? But you guys see what we're trying to do here? We're trying to represent what the actual shape of the carbons are. Because one of the key things, right, is that shape and function, shape and reactivity go together. It's important to understand that a triple bond is linear. They behave in a different way. We're going to talk about sterics as we go through this semester. And that's going to be important. Sterics say, what are the bonds in the environment around these atoms? Okay, what's the geometry around it? And alkynes, triple bonds, have a unique geometry that we can do different chemistry with. Okay? Now, we can put that triple bond in different places, right? We can make rings with this. We can make double rings with this. You guys catch what I'm saying? Watch this, right? So C6H10. I don't like it, Dr. H. Well, what I'm trying to get you guys to think about, and one of the joys that I get out of organic chemistry is because, remember I told you, I'm not going to give you a lot of definitive answers, right? There's plenty of right answers in organic chemistry. I mean, there's plenty of wrong answers too, but we just have to not limit ourselves with how we think about things. Don't get so locked into just saying, I can only draw straight lines. Well, I can draw rings. Okay, what about two rings? What about rings with double bonds, right? What about a 5-membered ring with a 3-membered ring coming off it, right? All these different types of ways that we can represent how these carbons and hydrogens come together. And the other point being, how many molecules are there? Answer is infinite. Got it? How many of those infinite have we discovered? That, you know, in the grand scheme of things? Chemistry's been around for a while. It's not going to run out of things to discover anytime soon, right? And you guys can see that even if we have just a simple formula like C6H10, we can come up with 40 different ways that we can put that together, right? You guys following along what I'm saying with this? So we need to kind of expand the way that we think about things while you guys are walking through organic chemistry. Don't get so locked into things. And that's going to be a skill that we develop as we go through, right? As we practice this more and get comfortable more. Sound fair? What's up?
Can you do the stick structure again without the orange dots?
Yeah.
Sorry.
No, it's fine. I'll just redraw it down here. Good? We could also do 2 double bonds, huh? Ooh. Things take a turn. All right, yeah.
I have a question. With that one you just drew, why would there be, the one you just drew, yeah. Why would it be 2 carbons right there if it's like all just the same line?
So why are there 2 carbons here?
Yeah.
So at the beginning and the end of where we represent bonds is where carbons are, right? So this is our triple bond,
Because of
and then these have single bonds coming off of them. Right, this is one of the tricky things about triple bonds, okay? This isn't the carbon just here and here, right? There's 2 carbons here that are triply bound, and then we have the other ones coming off of that. Yeah?
Wait, how did you say you know that that one's right and the other one is wrong?
How do I know that this is wrong?
Yeah.
Because we're looking at what's the geometry around here? It's 180, so we try and represent that with our 180-degree angles here. Okay. Good. Let's do more, right? All right. So see if you guys can translate this into your carbons and hydrogens and all that kind of stuff. Okay. Draw out all your bonds to all the hydrogens, even the one on that oxygen. Yep.
This disgusting thing.
Mm-hmm. You're missing a hydrogen though. Oh no, it's just hidden behind there. Okay. Or you did. Well, let me see.
No.
So is this my nice complete drawing?
No,
No.
No.
that's what I first drew.
What did I miss?
Carbon on the oxygen.
Carbon on the oxygen.
carbon where the oxygen is supposed to be.
Carbon where the oxygen.
Bonded
They're
to.
bonded there.
It's supposed to be bonded to another carbon.
This?
Nope.
No.
This.
There.
No, it's bound to the hydrogen. Okay.
And
Oh wait, psych, never mind.
Yeah.
I went.
So, a couple of things. When we draw our shorthand notation, hydrogens are only understood when they are bound to carbon. When they are bound to heteroatoms, aka anything that's not carbon, we have to explicitly show the hydrogens. Everybody follow along with this? So when I have a hydrogen bound to an oxygen or a nitrogen or something else, we have to explicitly show it, okay? All the other rules are still the same. Where we have a bond between carbon and another atom, we represent that with a straight line, right? At the beginning and the end of the lines, or where they come to an angle, right, that's where another carbon would be. Everybody follow along with this? What very, very, very important thing did, ooh, very good, did almost everybody forget to put on their drawing? Let's see here.
Lone pairs?
Ah. Aha. You guys with me on this? Oh, you didn't forget, I'm sorry. Why didn't I have to put my lone pairs on the first drawing I gave you guys?
Because they're assumed.
Oxygen never breaks the octet rule.
Got it? Everybody follow along with that very important rule there. Okay? Carbon, oxygen, nitrogen, fluorine, they're always going to be obeying the octet rule. Okay? If they don't obey the octet rule, we have to put a formal charge on it. And formal charges are part of what you have to draw. Okay? So if I don't have a formal charge on there, what's my assumption? Everything is 0. What's the only way we can get a 0 formal charge on an oxygen with 2 bonds? We have to have 2 lone pairs on it. Everybody following along with this? This is important. Now, usually, right, and it would be in your best interest to just draw those lone pairs there. Why?
Because it keeps us from forgetting.
Day one. Keeps us from forgetting. Day one, what's Dr. H's rules to success in organic chemistry?
Don't skip steps until we have our PhDs.
Sort of. What does chemistry? So if you don't have your electrons explicitly shown, what are you going to forget?
The electrons.
Where they are. And what does chemistry? Got it? How does organic chemistry work? Something negative, find something positive. What's the only negative thing in the universe?
Electrons.
Electrons.
What about quarks? What about quarks?
We're not dealing with that stuff here. Okay? Everybody with me? This is important. Okay? Sometimes lone pairs are understood. Right? If we break the octet rule, right, then we have to put a formal charge there, and that's going to change how we draw our Lewis structure. Got it? But don't forget your lone pairs on heteroatoms. Okay? Yep.
What's the heteroatom?
Anything that's not a carbon. Okay. Here's what I mean. You guys ready?
It is not even 9:30 in the morning, Doc.
It's not.
What's that?
For the one right before, why would there be a fifth carbon on the end of the OH line? Because you said there's, every time there's a line.
Whenever we have to show a bond to that carbon, then, right? Or maybe I'm misunderstanding your like. Let me sneak around here a little bit. Look at your paper then.
So I thought, well, I did it this way initially, but like, wouldn't it be like another carbon bond?
Oh, no. So that's showing the bond to that oxygen, right? So if we don't have it, if there's nothing.
There's nothing written.
Exactly, yeah.
Thank you.
Mhm. Where's the positive check?
Well, because nitrogen.
Yeah, where is it? On your, remember, when you're drawing your Lewis structure, always show your charges, right?
Yeah.
There you go.
But it's just because nitrogen's formal charge is each 5, right? Yeah, that's why. Yeah.
Don't forget to explicitly show your charges.
Yeah.
Do your research. All right, so 3 carbons. All right, here we have our nitrogen. Everybody good on that? Oh, I forgot to put the 2 there, right? Yep, sorry. Okay? So just as a comparison, if you guys do that versus that, right?
That would be neutral.
Mm-hmm. So just, I'll really quickly kind of just do this. And we see we'd have that lone pair there instead. Got it? If I'm drawing this here. Everybody with me on that one?
Mm-hmm.
So always pay attention to your lone pairs, pay attention to your charges. Okay? What does chemistry?
Electron.
Gotta know where they are. Good?
Yep.
Alrighty. I will see you guys on Monday, because we don't have Monday off. No breaks for you guys.